So we're going to start the problems here for Chapter 3. So for the first problem, I have traffic lights. So I have two poles that are supporting them, and so here I have a wire from point A goes down to where the first traffic light is, say. This is point B. This angle here at this point, obviously we're going to assume these are sufficiently tight that these are straight lines. All right, and so the first traffic light has a 10 kilogram mass, 10 kg in there, that this is horizontal. This is then 15 kilograms, and here we have theta going off to the other pole. All right, our coordinate system is the normal XY coordinate system. And let me just say, if I don't put this in there, always assume that. Okay? Don't do something else bizarre unless I say you may pick whatever coordinate system you want. And there are times I've done that. All right? But if I don't say anything, this is the one to presume. Okay? So we went to, what do we want to do for this? Find the tension to support the traffic lamps. So we're looking for the tensions in here, here, and there. All right, so these would be three separate wires setting this all up. Okay, so the first thing we need to do, always, there is no exception, you shall always do this, is you need to do a free body diagram. And your physics folks would have drilled this into you. I reinforce said drilling. All right, so we'll start with just looking at the overall system, and we'll kind of go from there. So in doing the free body diagram, I'm going to break the chord here and break the chord there, and so that would leave me with what I will call FAB, 15 degrees, and I'm going to break off this traffic lamp and that one. So if I do that, then I'd have a force here that's 10 kilograms times 9.81 coming off there. And I'll just extend this over just to give myself more room. And then off of, that's point B, there's point C. That's to be 15 times 9.81. And then I got this chord coming off. I'll call that FCD. All right. And that has an angle theta. So we'll obviously need to figure out what theta is. All right. And if I look at this thing, I could sum the y forces and try to solve it, but I can actually, it's going to be a little bit of a mess here. So I've got, let's see, I could have an fx and an fx here, and so I'd have a relationship between these two. I'd have one in the y here, one in the y there, and then these two coming down. It looks like a lot more work to me. So I'm going to actually break this up again. I'm going to break it across here. And let me just comment further on this. If I look at this thing, I have two unknowns here, FABX and FABY. So there's two unknowns here, and there's two unknowns there. I know these two forces. Okay. So I've got four unknowns. I can write an equation in the X. I can write an equation in the Y. There's not enough information here to solve it. So that's why I'm going to just break it again and get it into a form that I can work with easier. So let's just do another free body diagram. Ugh, that was ugly. Okay, here's FAB. It's still ugly, but it's better than it was. And then I'll just put in an FBC going this way. And then I can also have an FBC going the other way. And where this comes down. 15 times 9.81. And here's FCD coming up. Okay? So and I have an unknown here in theta, so over here I know this is 15 degrees relative to the horizontal. I can solve this directly, because look at this. If I take the y component coming up here, FAB sine of 15 degrees is exactly equal to 98.1. Boom. So FAB sine of 15 is equal to, so this is just summing forces in the y. That's going up. Oops, that should be an arrow going down, equals 98.1. I can solve for FAB. FAB is now 379 newtons. I have the tension in that cord. Well, this is going down. That's just in the y. So since this traffic light isn't moving anywhere, it means this x component and that x component have to match. All right? So now I can go FBC, which is going that way, must equal FAB cosine of 15 degrees. Well, I can solve for FBC now, and that's 366.1 newtons. So now I have this. Well, if this isn't going anywhere, that tells me a lot. This is all in the x. That's all in the y. So FCD must actually equal what those are. So let's see. FBC, that's 366.1. So therefore, FCD must equal 366.1 along the x, right there. And then this amount along the y, which is 15 times 9.81 is 147.15 y, and that'd be all newtons. Boom. Now, what's the magnitude of that? No problem. So to get the tension, we take the magnitude of this squared plus that squared, square root. We would come up with 394.6 newtons. I'll let you check that out. If we wanted to get theta, real easy. Okay, the force is going along the wire, so you just say theta equals inverse tangent of the y component, 147.15, divided by the x component, 366.1, and that works out to 21.9 degrees. And there we are. So, easily done. Next problem. So what we have here is this is a bar, so it's rigid, and so it was originally up here. Okay, so this is 5 feet from pin to pin. So this is 2 feet long, so this rotated down from this position like so. And then here I had a spring. Okay, and so now the spring connects B to this pin over there. All right, and the spring constant is 50 pounds per foot. And hanging at B, the reason why it helped motivating it to come down is 80 pounds. So here I have a rod, and at the other end of the rod at point B, 80 pounds is hanging down, and then coming off of B is this spring, which has a spring constant of 50 pounds per foot. And we're told this angle is 60 degrees, and this is at equilibrium. So it came down and it went doing, 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 and eventually it stopped in this position. And it's all happy here. And so what we want to do, the problem says, find the unstretched length of the spring. Okay? So let's go about making that happen. All right. So free body diagram time. So I'm going to take this point B, which will be right here, and let's see what we have. We're going to have through this bar, and this will be at 60 degrees, I will have, let's call this point up here A, and this point here is going to be C. So I have FAB coming off. Here's B. All right. I have 80 pounds coming down. No problem. And there's some angle here, theta, and here is, we'll just call it F spring. Could also call it FBC. We're all just as good. All right. So let's just take care of some geometry first. I know this is 2 feet. I know this is 60 degrees. Therefore, this is 1 foot. 2 cos 60 gives 1 here, and that would make this, the vertical portion, 1.732. You should probably remember that the cosine of 60 degrees is a half. So 2 times a half is 1. I don't expect you to remember that. All right? So if this is 1, so let's think about this. This length here from here to here, all right, is 5. But this is gone over so that this distance, if we to follow that down, is 1 foot. That means this distance here must be 4. Okay? Oop, I made a mistake. I was just looking at my notes. This isn't 5. Please change this. This is 4 feet. All right, so this is actually 3. All right? A little bit of change. So if this is 1, that puts 3 over here because I had 4 up top. Okay, please note that. All right, so that tells me that this is 3 here. And if you think about this, okay, look at this vertical distance. They were horizontal, and this is 1.732 coming up. Therefore, that's 1.732. Just noting that. So just getting all my geometry worked out. So it tells me I can figure out theta. The tangent of theta is the rise, 1.732 over the run, which is 3. And if I back that out, I get theta is 30 degrees. Okay? So now I need to start solving some stuff. And this one's a little bit more tricky to do. Why is that? This is in the x and the y, that's in the x and the y. So I have enough information. I have an unknown here and an unknown there. 2 unknowns. I can get an equation in the x and an equation in the y. So I can solve this thing, but I got to do a little algebra. If I sum the forces in the y, that has to be equal to 0. Here I have this one going up, so I'd have FAB sine of 60 going up. And here's F spring plus F, let me just call it SP, I'm lazy. Sine of 30. All right, those two are going up, and here's this one going down, minus 80, and that has to sum to 0. All right, if I sum the forces in the x, all right, this is all in the y, so I'm left with the usual coordinate system. I'll just put it in now. So x is positive to the right, so this is in the negative direction. So I have minus FAB cos 60 plus FSP cos 30. And there are no other forces equal to 0. Okay, I have 2 equations and 2 unknowns. Got a little algebra here. As we go through this course, I expect you to get practice and do these things on your own. So I'm going to leave this for you to figure out. FAB, when you go to do the math, will work out to be 69.28 pounds. All right. And F spring, FSP, will work out to be 40 pounds. Now, I'm leaving this for you to do. All right. I hope you'll do it. Okay. And when we normally meet for this class, I have the students do a notebook, and I check the notebook, so I would make sure you did it. We're not collecting notebooks. That's impossible with doing the course online. But I'm going to urge you to do this. This is like, for those of you that play golf can relate to this, this is like a 3-foot putt. A lot of people, when they play golf, when they get the ball within 3 feet, they go, oh, it's a gimme, and they just pick the ball up and walk off the green and just add 1 shot from there to the hole. And then if they ever have to play in a tournament, they can't hit a 3-foot putt to save their life. All right? Same idea. Make sure you can do this stuff, because on an exam, it's not a gimme. You have to do it. If you don't get it, you get marks taken away. So do the 3-foot putt. All right. So we could solve for the force in the spring, and so we got this is 40 pounds. All right. And so what we want to figure out then is the whole problem was what's the unstretched length of the spring. All right. Well, 40 pounds is equal to the spring constant, that's the K, times the stretch. Let me call that stretch D, because X is the horizontal, so I want to use something different. All right, well, solving for that, I get D, the total stretch then is 0.8. 40 divided by 50. So there's a stretch of 0.8 feet. The question is what's the unstretched length? Okay. Well, so let's figure out what's the distance between B and C up there. So the distance BC is equal to 3 squared. Remember, we have 3 horizontal, 1.732 vertical. So the 1/2. And that works out to 3.464 feet. Okay. And that's equal to the unstretched length, which I'll just call length here, plus 0.8 feet of stretch, because the force is 40 pounds. So we just bring that to the other side, and we're left with L for the spring is 2.664 feet. And we're all done with this one. All right. Chapter 3 has one more problem. See you soon.